And you want to record it, right?
I did.
All right, great. So welcome, guys. This is our second GEM of the semester. I'll be presenting the flight dynamics portion of rocketry, at least. It's like a generalized thing towards rocketry, geared towards beginners, but it's also really geared towards certs members. So if you're interested in certs, this is kind of trying to like gauge your interest for certs. Definitely hit up some of the PMs and also the president and also Alex about that. Okay, so going forward, we're gonna start with what we left off. So last time Alex explained the basics of rocketry, the basic components of the rocket. He talked about stability, how the center of gravity and the center of pressure play into that. And then he did a quick open rocket tutorial. In case that there's any new people to this education meeting, I don't want to like hurt you guys or leave you guys like left off on that. So I want to give you guys like a really quick brief explanation of all those things. So a rocket is comprised of a nose cone, as you can see here, an airframe or a body tube, which contains all the components, and a fin, and a motor. A motor is what we described like the engine for it. We call it motors because I guess it's like the more scientific term for it. It's the typical term used for it in rocketry. So I think that's all pretty fairly self-explanatory. The other additional thing is if you want to actually get your rocket back down, you're going to need a parachute. So that'll deploy at apogee, or the tallest part in flight, and we choose that point in flight because that's the point in flight where the velocity, or at least the vertical velocity, is 0. So it's the slowest point in the rocket's flight, and that'll make it the least force intrusive part of the flight for your rocket. And that's really important because when the parachute deploys, it's going to tug on the entire system and potentially break it. Okay, so the other component that you taught is the stability. So stability is extremely important for rocketry. In fact, it's pretty much the only thing that the RSO, or like the safety officer at a launch site, is going to ask you. He's going to say, is your rocket stable? And the reason why he's asking that, he or she is asking that, is because if your rocket's not stable, it's not going to fly straight. In fact, it might just fly in any sort of direction. And stability is a really easy parameter to get down. So it's a primary design parameter for rockets. So the stability is determined by 2 components of the rocket. The center of gravity, which is the sum of all the masses on the rocket. And it's basically the point on the rocket where all the masses are. Or where all the masses or all the forces act on the rocket. So if I use a pencil here, it's really easy to find what the CG is. Pretty much all you have to do that is you take your pencil or your rocket, for example, and we literally do this on the launch site. We go like this, and we find what's the point that it balances on. That's the CG point, and that's where all the forces are going to act on the rocket. So for example, if I go here, that's not the CG, but right here is perfect. Okay. The other point of the rocket that's very important is the center of pressure. Now, the center of pressure is where all the aerodynamic forces are acting on the rocket. So, for example, where the pressure and the aerodynamic lift and drag are acting on the rocket as it flies. That's a different force from the center of gravity. Or a different point than the center of gravity. And that's largely dependent on basically your airframe and the fins, pretty much all the external part of the rocket, nothing internal. Right? So this is purely based on shape instead. And this is largely dominated by the fins. So basically, if your fins are big enough, you're going to be stable enough. And it's really hard to calculate in terms of, or it's a little bit more difficult to calculate than just balancing up the rocket. So it takes a little bit more analysis to do. But we have a really great simulator called OpenRocket to do that for you. So it shouldn't be an issue. In fact, I think OpenRocket's a really great resource for students and also just rocketeers in general. So definitely use it if you're interested in rocketry. I'm not going to give an OpenRocket tutorial yet, but we'll use it later in the presentation, and we'll give you like more of a background in it, and you guys should be able to pick it up as you go. If not, work together as a team. Although you can't do that through Zoom, but work together or ask questions. Feel free to ask questions about it. We're always here to help. So we have like 3 leads here to help you. So okay, so going forward, I'm gonna give you a quick outline of the presentation. So first, I'm going to start with Newton's laws of motion. Pretty simple. That's like the basis of where you do every calculation in rocketry, or not in physics and everything, pretty much. And we're going to apply it to the rocket and see what are the key assumptions that we use to like basically calculate all the things that we do. Then we're going to look at two major forces on the rocket, which are thrust and drag. And then finally, we're going to, and those really the majority of the presentation. And then finally, we're going to go into a quick demo where I explain how to use OpenRocket in terms of what I taught today. And then a competition where based on who does the best, I'll give you one of these special little swamp launch swag, which is like a little sticker. So yeah, so it's something that you win tonight. All right, so going forward, we got Newton's first law. So Newton's first law is pretty simple. It's an object remains at rest until acted upon. So key thing is for our rocket's not going to move unless we actually propel it with something, which is pretty simple. It's just going to stand there. But that basically necessitates a propulsion element, something to move it. It doesn't necessarily have to be a motor. It could be like a cannon, I guess, or you can literally throw it. But the key point is that it's not going to move. Second law is the forces acting on a body are equal to its mass times acceleration. Now, this is very important in terms of what we use or what a rocketeer or aerodynamicist would look at what's necessary for a rocket or for calculating this thing. Because with this one key point, we're able to derive all the rest of the components of the forces on the rocket. And it's a very key point. So for example, we know that, come back. So for example, we could say that F is equal to ma. Okay, so that's second law. And then what are the forces acting on the rocket? Well, at standstill, when it's just on the pad, right, it'd be thrust, which is the upward force, minus weight. And then our thrust is going to be given by whatever propulsion element we're going to use. So we're just going to say thrust is of a function of t. And then weight is just the mass times the acceleration of gravity, so just g. And there we go. Now we know, okay. Now we know like how much thrust do we need? We just need more thrust than the weight, which is pretty simple to make it go up. So once we know that, now we know what type of motor, what size or what power motor we need to use. And then something to keep in mind is that this mass is not going to be constant. It's actually going to decrease. So as the propellant goes down, or as the propellant is used, it's going to go down, and that's going to decrease the mass of the rocket very minimally. So you don't really have to consider it that much, but it's just something to keep in mind that they're both functions of time in that sense. Okay. All right, so then Newton's third law. Every action has an equal and opposite reaction. So all this means is that we just need a propulsion force to push the rocket into the sky. Oh, sure.
Are you going to connect to that?
Okay, so Leonardo asked, what was that?
Nothing.
Okay, Leonardo asked, is drag a major component to consider for motors? No, but it's a major component to consider for the rocket itself. But the reason why I didn't consider it there is because I considered it, I talked about when it's on the launch pad itself. So right now, since the rocket's not moving, there's no drag on it yet. It will be, and we're going to talk about that very soon. So, but no, it shouldn't be a component. It shouldn't be a component for the motors because for the most part, the motor is going to be inside the rocket. Okay, so pretty much all we need to know in terms of Newton's third law is that we just need a propulsion force to push it up, and that propulsion force has to expel velocity downwards. If we expel velocity downwards in terms of the propellant mass, then our rocket would go up in terms of its mass. And there's a famous rocketry equation called Tsiolkovsky's rocket equation, made by like some Russian rocket scientists that's considered the father or the grandfather of rocketry. And of course, he's Russian, because why wouldn't he? But that equation relates the velocity, the exhaust velocity of the propellant to the velocity of the rocket. So you can actually calculate based on that what's going to be your rocket's velocity off the rod, for example, which is very important for determining stability. Okay, so now that we know our forces, which are thrust and weight, Now let's actually characterize what thrust is. And this is a lot in one page, but it's very important. So thrust is measured in newtons. And obviously it is because Newton would obviously pick his own name. So, and as I said earlier, it has to be greater than the weight of the rocket to go up. And there's a wide variety of motors available. So we need a way of like actually distinguishing a motor from another motor to determine what it is. The way that we do that is we just use the motor's name within rocketry or the rocketry industry. So for example, here, there's the H283ST-14, which is a common insert motor that we use. So in this case, the H is the impulse range, or the, I guess consider that the power of the rocket or the motor. The 283 is the average thrust of the motor, which is measured in newtons. And then the ST is the color of the propellant. And then 14 is the delay grain. That's the amount of seconds from ignition that the motor will take until it finally expends its or shoots out its ejection charge. The ejection charge is what actually shoots out the payload. So just think of it like a little explosive that goes off in the airframe that's contained at least, but it'll basically separate the rocket, which allows us to deploy our parachute. So this is kind of nice, but we need a little bit more information in terms of how do we actually determine what motor is better than the other. So what we'll look at are thrust curves to determine how the motor is actually going to behave. So here on the right is a thrust curve. I'm not sure if you can see that. I can use the annotation. So here on the right is a thrust curve. You can see it's changed with time. So let me show you that graph in a little bit bigger scale. So like I said, the average thrust is going to be around here, right? Which is like that 283 mark. Now notice it's actually not 283. That's because aerotech motors aren't very good in terms of actual accuracy. There's a lot of variety in them, but this is the measured thrust from a flight, right? And then the key thing you need to notice is not really the shape is pretty important in terms of how it's going to act. So if you could think of it like this, or if you can imagine on a flight, and it'd be nice if I had a video, or if you came to a launch, you could see it. But if I was to fly this motor, it basically act like this on the launch pad, then 3, 2, 1, very fast. It's a very fast burning motor. And that's because this axis right here is only 0.7 seconds. So that'll tell you that it pretty much just shoots up immediately. All that force is generated and pushes the rocket up very, very fast. Meanwhile, if I look at another motor, this motor, for example, is over 3 seconds range. So, so it does a lot less in terms of the actual average thrust. It's only 80 newtons of thrust. So it can really carry like a 80 newton weight rocket, but it does that over a longer range. And there's a lot that goes into like, okay, what's the better motor in that case? And also in the terms of the H283ST, well, that motor is really freaking strong. So if you don't have a very strong assembly or very strong structure to carry it, then it might just shoot straight through your rocket. So that's not very good. You definitely do not want to let that happen. So in this case, the difference between these two motors is that the burn times and the power itself, or sorry, the force itself are completely different. However, the thing that's uniting these two motors is that they both have the same impulse. Yeah, so impulse is actually the measure of the power that the rocket has, or the motor has. It's the force times time. So if I think of it like this, it's actually the integral of this graph, or everything below here like that, right? And it represents the area under the graph. So these two motors actually have the same power. They could carry the same type of rocket, but they have a different amount of actual like altitude in terms of what type of rocket they can carry. So if I were to fly the same rocket, or sorry, they'd actually have the same altitude, but they'd have a completely different flight type. So you have to consider that in terms of if you were to fly the same motor in a different rocket, how would it do? Right. So then the question you have to ask yourself is, does more impulse equal a higher altitude, for example, right? Okay, so that was a lot about thrust, but now we have to consider drag in terms of how that works. So when the rocket's actually flying, sorry, let me just turn off this edge. There it goes. So when the rocket's actually flying, it's going to produce drag on the rocket. So when we return to the F equals MA here, right? And we have thrust minus weight. Well, when it actually starts moving, it's gonna produce drag on the body, and that's gonna slow it down. So if you have a very fast moving rocket, it's gonna produce a lot of drag, and that's gonna slow it down. And we have to measure that between the motor that we select, and and also the weight of the rocket itself. It's just a bunch of parameters that we have to find the fine line between what's the best one. So drag can be described as the actual resistance of air against the body of flowing through it, or the rocket flowing through it. And this is a very difficult parameter to calculate. It's something that people spend their entire lives analyzing. And if we're talking about planes, and then also on this graph, or sorry, this diagram, for example, we'd also consider lift. Lift is also the same thing as drag, but just instead of being actually down against the rocket, it'd just be up instead. So we wouldn't consider lift in this case, for rockets at least, because so long as you're stable, pretty much the lift is negligible in terms of it's pretty much just a tiny little fin in the back. It's not actually going to move it a lot. What it is going to do though is to keep the rocket flying at least straight. It's not going to actually move the rocket up. Another way to think of that is a rocket flies pretty much perfectly up, while a plane would be generating a lift force going horizontally. So it's a completely different problem. This really depends on how you view it. Okay, so this is the famous drag equation. It's pretty daunting at first, but once you break it down, it actually makes a lot of sense. So first thing to consider is that it's using the cross-sectional area of the rocket, A, here, and the velocity squared, right there. So what that really tells you is that both of these parameters for the rocket are squared values, meaning that the drag on the rocket is going to be squared times that, so, or quadratically related. So if you, for example, increase the diameter by 3, it's going to increase it by 9 instead. The drag by times 9. So it's going to be extremely like a large difference in drag, and it's going to slow it down a lot. Same thing with velocity. The more fast you go, the more drag you're producing, the less efficient your flight is going to be. The other thing to consider is the actual fluid it's flowing through. So if it's flying through air, for example, that's going to be a lot different if you're flying through honey. So that's where the density rho comes in, or right here. That's there as well. And the CD, which is going to be largely dependent on the shape. So I talk about that here. Also bring up compressibility, which is not as important for this application, at least, because you're not going that fast. But if you were to go fast, the air would actually get more dense as you go faster. So the key takeaway from this is that going faster is not always the best, because it just kind of slows you down at the same time. Another thing is angle attack, which won't be discussed here as well, but I'll just briefly mention it. That's the angle between the wind flow and the rocket's direction. So if the rocket, for example, has a large angle attack, that's going to produce even more drag on the rocket. You shouldn't be really worried about that, because that's not a huge consideration for the rocket, at least at this point. Yeah, so think about it. If I were to increase the area on the rocket, for example, right, is a circle, right? And we're considering the area of this circle here. So the area of the circle is A equals pi r squared, or A equals pi d squared, or 4. So now if I increase the diameter by 2, then the area is going to increase by 4. That makes sense. And the same thing with velocity, except I don't have a whole area. So yeah, there you go. It's main thing you have to take away is that the more you the faster you go and the more bigger the object is, the more it's going to slow down, obviously, right? But now we can quantify that using Newton's laws. Okay, so considering the drag coefficient, that largely depends on the shape of the body it's flying through. So if you're to throw a cube through the air, it's going to go a lot slower if you're to throw a football, for example. That's what the coefficient of drag really shows you, is how does this object actually act throughout the body. And you can really see that here in the equation, where in the equation, there's not really anything talking about the shape of the body. It's just area. So we're just considering a circle in this case. But what tells you how a different shape the rocket would look like? What if I had a rocket with also a circular airframe, but it had a completely different nose cone, or it had a different shape to it entirely? Then we'd have to consider, how does these two things act? So that's what the CD kind of like ties it all together. It's kind of like a easy number that aerospace scientists just kind of like threw in there just to like kind of solve the rest of the equation. So you'd solve, actually, if you know the drag from F equals ma, which this is just another force, that you solve for CD. And that's how you can get the shape. And that's what they've done on the right, is that they basically put all these shapes into a wind tunnel. All these shapes on the right, on the wind tunnel, and then they solved backwards to get the drag coefficients. That's what we're doing on IRAC right now, is that we're trying to solve for the drag coefficient of our rocket, doing the same way. But instead of using a wind tunnel, we're just gonna fly the damn thing and see how it goes. So this can be broken down to two types of, or three types of drags. Okay, so there's pressure drag, which is axially, which really depends on that shape that I told you about. But then there's also another type of drag called viscous drag. That's basically the friction on the body. If you have a really hairy surface, for example, like I guess my arm, it's not going to be as good for, or as aerodynamic as if you had like a, if you had like a completely smooth surface. So you should really, I guess that's like the best analogy for that is like I guess like a swimmer. A lot of swimmers like actually shave all their hair off, wear like those little caps. That's purely to just reduce the viscous drag that they have on the water. And then that's going to be acting parallel. So if you have a shorter person, for example, you're going to go through that pool a lot faster than if you're someone who is like long and lanky. Well, that's not really true for the US, I guess. And then wave drag is something you have to consider if you're going really damn fast, is that you're actually going to produce shock waves on your body, and that's going to slow you down more. I'm not going to go into that more, but if you're taking compressible flow, you learn all about that. So yeah.
So why is it not one of those figures on it, but why is it still below that?
Okay, so it's actually from 0.8 to 1, from Mach 0.7 to Mach 1. After that, there are effects similar to wave drag, but it's mainly when you're going through that transonic region where those wave drag effects are happening. Because what's going on is essentially at the front of your body, there's no shock wave. At least, like, I'm talking like at the nose cone tip, there's not really any shock wave because you're still going at 0.8. And as it travels through that body, and as your body kind of squeezes the air, think of it like going through think of going through like a pipe, and the pipe is squeezing it, or like your thumb going there. That's a compressibility effect. That's actually accelerating the air past the nose cone, and that's what's going to produce your shock wave. Is actually the shock wave. And then the other thing that's going to produce a shock wave is the fact that you have a fin. The fin is like a big old protrusion right there. That's going to cause a huge shock wave to form, and it's going to slow your thing. So what's happening, and you're learning compressible flow right now, and also for also I don't know everybody's not taking compressible flow. So in general, what was happening in like the 60s and like 50s, when they're trying to go like past the shock barrier or sound barrier, is like essentially all these like airplanes, all these pilots are like taking these airplanes, diving down to basically go as fast as they possibly can. And what's happening is basically the entire freaking plane was just disintegrating, and then they die because essentially they didn't figure out that wave drag was a thing, and that sound barrier was just a cause of their design. So it's really important to consider in terms of choose a design that does not stick in that transonic region. Because if you can go after that transonic region past Mach 1, then you're just supersonic throughout. Those shockwaves aren't as big of a deal in terms of that. You still have shockwaves forming on the body, but they won't be as like structurally they'll be as structurally significant in terms of, okay, they will still be performed made or sorry, they'll still form, but out of protrusions on the body and not like out of like just like a sheer thing. It's mainly that barrier of Mach 1 where you find them. Yeah, it's also why when we're designing our rockets, we don't like to stick in 0.8. We'd rather be like, or we wouldn't want to go like 0.9. That's terrible. You're like right in that region. You're like making it worse. You might as well just blast through that.
Yeah.
So
Also, like as an aside, most of our rockets probably won't go faster than 0.6.
yours now, ours do.
Yeah, most of the SL rockets, they don't go very fast. They'll go maybe 0.6, maybe 0.5 max. If you're building an L1, they'll go like maybe 0.3.
Yeah.
They don't go very fast generally, unless you're doing at least a level 3.
If you're doing a cert, why not, bro? Just take it there. Like go past Mach 1. Why not?
Pretty sure the motors don't allow it.
Make a smaller rocket. Make a smaller rocket. You're just they're really like constrained by that drag coefficient. But if you turn down like that body diameter all the way down to like what the motor is, basically just build your rocket out of the motor tube. It's a little like off track, but if you just build it as the motor tube, you're basically shooting like a pencil into the air. Yeah, you can get there.
Also, like why different shapes of nose cone matters at higher speeds. Because
Right,
it affects,
which we'll get into that.
Yeah, it affects the aerodynamics.
Yeah, so, okay. Still answering? No. All right, so this is a question for you guys. So which one of these car shapes are going to be more fuel efficient? And I'll just like open it up to the room to this way. I don't know. I hope they're not drag coefficients. Those are pretty big.
I'm all per gallon either.
Oh yeah, probably not that either. All right, so name like one attribute of either of these cars. If anyone wants to just raise their hand or go, we're on meet on Zoom. That basically determines their drag coefficient based on what I said earlier. On the left is the Honda Insight, which is my favorite car because it's the most aerodynamic car produced until the Tesla. I think Model S or something like that. Yeah, I know. You should bring that up. But it has the lowest CD. I think a CD of like 0.25 or something. And it's like it was made in 2000. It has like a mile per gallon of like 60 miles per gallon, which is fucking crazy. Excuse my French, but like this is a super cool car. And then on the right is like the opposite of that, which is a Hummer. So it's not quite, yeah, it's not quite that. So we should bring that up too. That's another important characteristic of it. It's a freaking square. So yeah, go ahead if anyone wants to take it. Huh?
Yeah, yeah.
I
Can I
think they do. Oh, my audio on? No.
Just in case I'm-
Good point. Good point. Go ahead.
Do you guys hear me?
Yeah.
I was gonna say that the one on the right, it has a lot of like blocky surfaces, making it very hard for the air to travel around without like, seriously dragging down the car. Like on the left, it's almost like an airfoil.
Hmm.
So the airstream doesn't break.
Yeah, exactly. That's actually what I was gonna do this in a little finger right here. So if you think of like the air traveling to the inside, it's gonna go right over this and then streamline over like very nicely while the damn Hummer is just gonna, and I'll do another color. Just go like strip hits it here, and has to go up, and has to hit the windshield again because we're American, and then it goes up. So this is not a very smooth shape at all. And that's the main thing you have to consider in terms of drag is like it doesn't really matter about like the shape, like it's a triangle or a cone. What really matters is it's smooth or continuous if we're in calculus too.
The one on the right also has a lot of extrusions on the top. Like it has
Yeah,
a little
extrusion is
bunch
very
of
important.
things.
So here, get the headlight. What else? You got one here, got the doors. Like these are all extra things that like I know it makes sense to have these things because it's a car, but like at the same time, if you're like trying to go really fast, it's not very good. So this is not a very good race car. And neither is the Insight because it's probably like running like some like low engine. But I kind of want to like engine swap it, take it there. But anyways,
Like even the door handles like
yeah.
flush with the body.
Yeah, right here. Yeah.
To decrease drag.
You notice the wheels actually like the rims are like completely messed up. Or not messed up, but like they're completely smooth. And that's to also reduce drag.
Oh shit, damn.
Yeah,
That's
no,
pretty good. You see that the
probably-
one on the back is even covered, so it's like the air doesn't get trapped in there.
right, exactly.
So why don't they do that anymore?
Huh?
Like the back wheel.
Like in the newer Insight models, because they're like, I think this car didn't sell as well because it's like too aerodynamic.
I'm trying to change that tire. in this thing.
Yeah, this car is actually it was like like fangirling about like the car, but it's like everything is like optimized, kind of like how like GMS optimizes their like car in terms of like weight savings. Everything in there is optimized for like the lightest possible configuration in terms of a car, and then also aerodynamics. It's such a beautiful car. Oh, what are you talking about? Isn't it just dreamy?
It's like a Civic, but you
It's
get
like a
rid of the
s-
second door.
Oh my god. Yeah, I don't even, I think it's like a two-wheel car too, or a two-seater. So, yeah. Anything else that we can point out in terms of the aerodynamics?
It has a smaller cross-sectional area compared to the big car.
Yeah, exactly.
Trailing and the wall.
One on the right is very tall compared to the one on the left.
I didn't even think about that, to be honest.
Also the trailing end also influences like aerodynamics. So like, I don't know if you ever stare at 16-wheelers, but sometimes they have on the back of a 16-wheeler, they have a little like
You're not in the video, by the way,
I
so,
know.
so they can't see it.
You guys, but
Okay.
the
Not the
16-wheelers,
zoomers.
sometimes they have like these little plates on the end of it, which like helps reduce the trailing drag of the 16-wheeler.
Hmm.
So pretty, huh?
18.
18?
I know this is really bad to mention, but like if you drive like behind like an 18-wheeler, you can get pulled in.
Have you,
It's like an extra like mile per gallon of it.
well, have you seen like guys on just bikes sitting behind a semi truck?
People do that?
I've seen a video of a guy just like sitting on the middle of the
Just
bicycle.
coast.
Yeah,
Oh,
you can just
that.
coast behind it because it blocks all the
Yeah.
traffic.
Fuck that though. You're on a bike.
You're
You're
going 80 miles an hour. on
Screw
bicycle.
that. Okay. Yeah. I don't think there's anything in particular, but I think you guys get the drift or the drag, I guess, of like what's going on here in terms of the shape really determines how fast, or not how fast, but how efficient these guys are going to be. Now, if these were rockets, for example, right, if you build a little booster in there, this one would be a lot faster. So the same booster at least.
A spoiler on the head.
Yeah. All right. So does anyone else have any other last comments before we go through? Any already questions in terms of that? Okay. So in terms of rockets, just getting back to rockets, because we're not freaking GMS. So two things you have to consider are the nose cone shape, as Joel had mentioned earlier. So on the right, you can see that there's four configurations here. We have like a really blunt nose cone, which is literally just a rectangle, which you'd never freaking fly. But the other three are pretty important to consider. There's a cone, there's an ogive shape, and there's a parabola. Now, why is the parabola? If anyone can like figure it out, why is the parabola in terms of like a science or a calculus way more better than like the cone, for example? But you think like a sharp object would go faster than like a parabola? If anyone wants to try that.
Is it about speed or structure?
It's not shape. It's about the curve. Yep. It's literally just because it's continuous. So long as it's continuous, at least at subsonic ranges, then it's the better configuration. However, let's consider supersonic ranges, right? What's going to happen at supersonic ranges is that this is going to form a bow shock. Ooh, a bow shock like this, right? That's worse than if you made a normal shock like that, or not normal shock, but what's it called a wave. Oh yeah, I'm sorry, I forgot the name of not a normal shock. Huh? Oblique wave. Yeah, there you go. Oblique wave or oblique shock wave. Which is way, yeah, I know, way better than a bow shock, right? So that's what we have on the left is for higher Mach number ranges, non-supersonic, we have these whole range of cone shapes, and you can see that none of them really are the best. Actually, you know, I think one of them is the best. I think Von Karman's pretty much the best throughout. The numbers actually are tier lists of the nose cones based on like what's the best for that Mach number. So for example, for Mach 0.8 to 1, all of these guys are pretty much the best, but like these guys This one's the best. So really, I mean, this is not really considerations because we're not a hypersonics team for some reason, but well, for some reason, but if you guys want to do that, it'd be pretty cool. But what you notice is that basically the von Karman's one of the best. And then also this power rule rockets also, or nose cone shape is probably the best in terms of Mach number. And that's for the bow shock reason that I mentioned earlier. Now, to be honest, what you're probably only gonna be able to buy are these three: von Karman, Ogive, Cone. And we only have these two in terms of what we have available for certs. I mean, obviously we can always order more, but that's why would we? In terms of that, the Ogive is usually the most bought within rocketry, or at least like hobbyist rocketry, because it's the easiest shape to make. It's basically take a circle, then you go like that, and then you go like that. That's an Ogive right there, or a tangent Ogive. It's actually a very easy shape to manufacture. The cone's also a really easy shape to manufacture, which is also why it's the other one. And then the von Karman traditionally is the least drag producing nose cone in shape. Yeah.
I'm pretty sure bullets are made in the shape of one Karman, like high caliber rifle bullets.
Yeah, so this also applies to bullets. If you guys want to make weapons too, this is the team for you. All right, so
What even is the von Karman shape? Is it
that's a very good question. I should have had it. I should have had it. I'm really mad I didn't. I should just show it to you one day if you're in the lab. We have like von Karman's.
Hack is also von Karman if you make one of the variables zero.
Yeah.
It's completely
No, von
different
Karman's
shape.
zero. Hack is hack is like 1 or 2.
Yeah.
It's like it's part of the equation. It's just like a C. Okay, I'm not gonna draw it for you. I would, but it's literally just a different curve. I'll search it up, but not yet. Okay, so going forward, just like that. I mean, I'm not. You still want to put it on the screen?
It's like such a minor like little detail. that
Yeah,
you
yeah.
have, like-
You guys can search it up. It's not crazy. Okay. Okay, so the next thing we have to consider are fin shapes. So there's 2 types of fin shapes I want to discuss here. So first is actually like the planform area fin shape, or like the fin shape that you'd cut out on the water jet if you're part of rocket team, or on a bandsaw if you're some like, I'm not gonna say that.
Rocket 2 years ago.
Yeah, rocket team 2 years ago. So the one you probably don't want to make is a rectangle, but it's probably the easiest one. You could probably just like buy like rectangular shapes. It's pretty lazy to use, but you know, it'd work, right? You just need it to be stable. So that'd work. But I think the best shape in terms of actual aerodynamics is definitely going to be the clip delta. And that's the one that we usually prefer for subsonic flights. And then another thing to consider is the elliptical. You took compressible flow. Do you want to explain why the elliptical is the best, or have you not got there yet?
So
Oh, you're taking it. Has he talked about the Spitfire yet?
no.
Oh, okay, you'll get there. Sorry about that.
Yeah.
Yeah, okay, so basically, I should have a picture of it, but the Spitfire, if you guys want to go on Google real quick, is like a British airplane from World War II. You've probably seen it somewhere, like, but the main key thing is that the shape of the fin or the wing is like this, and it's also like that. So it's a really hard shape to make, and that's why the British kind of having a hard time making like those planes. But it's actually the best in terms of economics and efficiency. Not economics, but in terms of efficiency and drag. That's because it's actually the most aerodynamic shape, once again, because it's the most smooth and continuous. But in terms of a rocket, it's not the best, because what's better in terms of going fast is actually sweep. And sweep is when you take this rocket fin and it's like this, and then you take it down, you sweep it down like that. And you're gonna learn about this in, I keep saying that, but this is very applicable from compressible flow. But essentially, if the wind's going this way, it's actually going slower against the fin. I didn't do the vectors very well. Going against the fin, like that. And then there's another one going like that way. Actually reduces the wave drag on the fin, and also makes it less drag as a result. Oh, it also improves the stability for the converse reason, because now there's more what's that, how do I call it, more lift produced as a result. Okay, and then the other thing you want to take into account, by the way, do I have any chats? I have the chat open.
This one popped up.
Okay, does it
We also
lower
have a simple fact ready, by the way.
530? Oh shoot, okay. Okay, in that case,
Once you get kicked out, afterwards, fine. I assume no one can take it.
Okay, well, I hope no one takes it, but yeah, we'll keep doing our competition. I didn't realize that. My bad. Okay, so the other thing we have to consider is this is the last slide actually. Well, that's the last slide. So the other thing I want to consider is like actually the edge hitting the air.
Leading edge and trailing edge.
The leading and trailing edges, right? So as you can see for subsonic, the best thing is the smooth configuration or a rounded edge. So if you're making a cert, for example, just take 10 seconds or not 10 seconds, 10 minutes more like to just like really like just freaking sand the hell out of that freaking leading edge. That's gonna do a lot in terms of your aerodynamics. And then the trailing edge for all of them should be sharp in some configuration. That's because you want it's for the opposite reason. You kind of want to prevent wave drag for that for there. So remember that the airflow is actually going to speed up as it goes through. So that's where you want it to be a sharp edge. Last thing you have to consider, this little actual fillet between there. If you don't add that to your shirt rocket, you're actually reducing the strength significantly because what can happen is fin flutter, which is basically take a fin, for example, and it goes really freaking fast. It can start like actually oscillating like this, and then eventually if it oscillates too fast, it just snaps off, and that's not very good. You should search up a video about that. Fortunately, I don't have enough time to show you guys, but it's a really important effect that you guys should take into account. I think both teams do, and I think Matt's working on it, or Matt worked on a simulation for that too. So very important things to consider. The fillet, for example, also adds additional cross-section area. So, you know, you're sacrificing your drag, but you're increasing a lot of the structural strength. So it's not all about, you know, how do I make this thing go as fast as I can? You also have to consider, you know, how do I like not have a rocket turn into a missile? So very importantly consider that. Does it lower the center of pressure? The sweep? Yes, it does. It actually pulls down the center of pressure because you have more fin backwards. I think that's what you're referring to in terms of sweep. Okay. Sweet. Okay, so that was a lot, but I'm going to provide a OpenRocket file on Slack, right? And what I want you guys to try to do is improve the aerodynamics of the rocket using OpenRocket to get the highest altitude. So just like we would want to do with certs. So the winner gets one of these stickers, right? And if I don't find you now, I'll tell you, come to the lab sometime on Wednesday or Monday when I'm there. I'll just hand you one of these as a reward. The only limitation is that you must use an H motor or less. You must limit the motor to the diameter and length of the motor tube, which I'll show you how to do that. And the only thing is that it must be buildable shape and it must be stable. So I'll show you that here. Am I streaming my screen or just the presentation? Yes, I'm just share. You share screen, share.
When are you gonna make it?
Oh, like
It's optional.
15 minutes.
Oh, it's today.
Yeah, this is a competition. You gotta go.
Oh.
So let me turn this in or save this. Got it, put it to you. Oh wait, let me just show you how to do this first. So here's our OpenRocket shape or rocket. It's not very good, as you can see. It didn't follow any of my instructions, like I just said in this lecture thingy.
In like 5 minutes.
No, I did it very intentionally like this.
Okay.
Yeah. As like a not very good motor in here, but let me show you how to do two things that's very important. So first off, you go here, you can change the material, right? You can change the component finish, so how smooth it is, and you can this sets it for all of the components. And then you can change the mass here, although I wouldn't do that. I'll just keep using this component material. You can change the thickness though, that's available to you. You can change the diameter, you can change anything that you would like on the rocket. What else? For the motor, oh no, not that. I don't want to show you. For the fins, you can change the sweep length here. You can change the fin cross section area and also the airfoil. You can make the actual fin an airfoil instead of a just rounded. Fortunately, you can't do a diamond shape, which would be what we're using on on our rocket, on our X rocket. But hey, man, that's why CFD. That's why you have to use CFD. And then what else I want to show you? Yeah, the motors. So this is how you actually select the motor here. You go to motors configuration. You go to select the motor. And then you have this whole list of motors that you can use. Just make sure that when you go to manufacture, you press clear all, and then you press Aerotech. That limits you only Aerotech motors. And then you go here and you put this down to impulse, and you put impulse H. And then you just press these two things right here. Limit motor diameter and limit motor diameter to mount, and limit motor length to mount length. And then finally, you can go to the simulation, which I already have one prepared for you guys right here. Go edit simulation. All the settings should be good to go. You simulate and plot. You can plot it. You can see that, okay, it doesn't go straight up. It goes pretty straight up in terms of, if you look at this axis, it's only half a foot away from the launch site, which is, I wish we had that more in real life, but no. So yeah, as you can see, it just goes kind of straight up, and then that's the altitude where it deploys the parachute, and then it slowly just drifts down. Okay, so I'm gonna share this on the Slack. Give me one sec.
Right, just about done. I'm just gonna stop recording if you are.
Oh no, we're gonna do the competition thing.
You want to record it?
Yeah. No, oh, actually, nah.